थोड़ा इसको जरा ऊंचा करेंगे. हेलो हेलो, थोड़ा सा और. हेलो हेलो. ओके. इधर से. हेलो हेलो हेलो. थोड़ी सी और ऊंचा हो सकता है.
इधर से आप उधर से फुल कर दीजिए वरना शोर.
अच्छा चलो ठीक. Hello. All right, so today is hopefully going to be our last lecture where we will discuss the double slit interference pattern. As you know that if we have this screen A and a screen B, and then we have electrons coming in, or photons or neutrons or protons, or any subatomic particle, what we observe are double slit interference patterns. And these patterns have a definite mathematical relationship that is given by the intensity I equals some constant I naught sine squared delta over 2, where delta is given by k d sine theta over 2, right? This is something that we've already derived. And how do we define theta? So if you would like to find the intensity at some point, at this point for example, we draw a normal between the screens. We draw a line between the center and this point. This angle is theta. So this is something that we've already derived, and d is the spacing between the slits. And for interference to work, the slit width has to be of the same order as the wavelength of the matter waves associated with these particles. And this d is the slit width, whereas this k is related to the de Broglie wavelength of these particles. So this is something that we've already derived. Now we are seeing an interference pattern. By looking at the interference pattern, which builds up over a long time, can we tell what the wavelength of these particles is? What the wavelength associated with the matter wave associated with these particles is? Yes, because we can tell what the fringe width is, we can tell what d is, we can tell what k is, d is known, theta is known, we can tell what k is. So by looking at these interference patterns, we can find out what the value of k is. Hence we can find out what the wavelength is. Okay? Now suppose I give you the task of finding out the wavelength. By looking at this pattern or by looking at this equation, can you find out the wavelength in terms of for example, if this is the central maximum, this peak, you will find a minimum, the first minimum at a certain angle alpha. By measuring alpha, can you determine what the value of k has to be? If you can measure alpha, that is the position of the first minimum, can you please write down what the value of the wavelength or k would be? Alpha is the position of the first minimum. Find out the wavelength. So the best way to prepare for exams and for quizzes is to be attentive in class and do the problems that I assign inside the classroom. That's the best way of preparing for a quiz. Sorry?
Cos square theta.
I not cos square.
Sorry?
Isn't that I not cos theta? I not cos square.
Okay. This is I naught cosine squared. Thank you. So what is the intensity at the first minimum? What's the intensity? 0. So when the intensity is 0, cosine square of the argument has to be 0. So what has to be the argument? The argument has to be pi by 2, because cosine of 90 degrees is 0. So the argument equals pi by 2. Can you find the wavelength now? So at the minimum, at the first minimum, that is this point P, I equals 0. Therefore, this object has to be equal to 0. So KD sine of alpha over 2 equals pi over 2. Which means 2 pi over lambda d sine alpha equals pi, which means lambda equals 2 d sine alpha. So by looking at the neat double slit interference pattern, one can tell what the wavelength of these matter waves is. Alright? So if one can tell the wavelength, one can tell the value of k as well, which is the wave number. If one can tell the value of k, can one tell the momentum of these particles? Yes, because P is simply given by h bar k, or h over 2 pi, h over lambda. So if one knows the wavelength, one would automatically know what the de Broglie momentum is. So there are particles coming in between the screens. They are acting like a field, they are acting like a wave, and then they fall onto this screen as individual discrete particles. They form an interference pattern, and if this interference pattern is observed, there is a definite wavelength, there is a definite momentum, in other words, which means there's a precise momentum, and there's only one value of momentum because it's a neat, clean interference pattern. So there is no uncertainty in the momentum. But do we really know which slit the electron or the photon has passed through? No. We have no clue whatsoever which slit the electron has passed through. So we do not know the position of the electron. So this is also explainable with the help of the uncertainty principle. We are seeing interference patterns, which implies that we have a precise momentum, a precise wavelength, a precise value of k, but we do not have any which way information. We do not have any information about the location of the particle. Okay, so this is a manifestation of the uncertainty principle. The observation of fringes is explainable by the uncertainty principle. G.
So can we carry out this double slit experiment with just one photon at a particular time?
Yes, indeed. Just like with electrons, with photons we can carry out a one photon at a time experiment. With any particle we can do that.
Has it been carried out?
Yes, indeed it has. We carry out in our laboratory as well. It's not a problem. You just need a detector that can click when a single photon hits it. So this is explicable or explainable by the uncertainty principle. The converse is also true. If you would like to find out where the particle is, you would like to place a telescope at the position of the slits. The same arrangement, only that this time we have a telescope that is focused onto this slit 1 and a telescope that is focused onto the other slit 2. Now will we observe an interference pattern? No, the interference pattern is going to be washed away. So we'll observe something to this effect. Now we do not know anything about the momentum of the wave because we're not observing an interference pattern. We know nothing about the wavelength of the particles, of the field. But we do know which slit the electron has passed through because either this telescope is going to click or this telescope is going to click. Now we have obtained information about the location of the particle or the x value of the particle. So if this axis is the x-axis, either a click is observed at the position of slit 1 or a click is observed at the position of slit 2. So in one experiment this is going to click. In another experiment this is going to click. So with time a histogram is built. Clicks are going to be observed on 1 as well as on 2, but at any one time only one of these collectors is going to be operative, is going to click. So we have obtained information about the x position. We have reduced the uncertainty in x. We are now more and more certain about x, which slit the electron or photon has passed through, but we have washed away all information about the momentum. So this experiment that we've seen in so many different ways over the past week is also explicable or explainable by the uncertainty principle. You want to know more about x, you become more and more uncertain about p, and becoming more and more uncertain about p means that there is a larger realm of possibilities for p. You become more and more certain about the momentum, you lose your certainty about the position. There are more and more possibilities about the position. G.
Why don't we find the velocity and therefore the momentum by finding the time difference between the click at the telescope and then where it hits the screen?
That is also not allowed by the uncertainty principle. I have an example to show that as well. Okay, that's not allowed either. Alright, so now let's suppose I do, we've also seen the delayed choice experiment by the way. Let's do another variant of this experiment. Suppose I have again the two slit experimental arrangement. I have the two screens. I call this screen A, I call this screen B. And now once again I have electrons or photons or protons coming in. And I only have one telescope. That is aimed at this slit, that is tightly focused at this slit. Only one, and I have nothing here, I have no observer here. Okay, one thing I would also like to tell you by looking at these experiments, first of all, when you are detecting, the wave collapses into a particle or the field collapses into a particle. When these electrons are being ejected from some source or photons are being ejected from some source, they are being ejected as particles. In between, there is a field. Now, just by looking at the top arrangement and the bottom arrangement, we're just observing in a different way. The top arrangement does not have the telescopes. This bottom arrangement does have the telescopes. And these experiments are giving different outcomes. They're different experimental outcomes. Now one would assume that if you don't consider these telescopes, these observers, the two arrangements are totally identical. Just placing in the observers makes the experiment a different experiment. So this is another interesting feature of quantum mechanics, is that the observer is not a disconnected and a disenchanted bystander. The observer becomes a part of the experiment. Okay, the measurement apparatus becomes a part of the experiment. In fact, if you're a human being and you're looking at the flashes that are registered on the screen of this telescope, then your consciousness, your brain, your optic nerve, your eye becomes a part of the experiment. So the measurement apparatus, the gear that is observing or measuring something, becomes a part of the experiment. So this experiment is different from the above experiment, even though the arrangements are the same and they only differ in the positioning of the telescopes. In one, the telescopes are absent, and in the other, the telescopes are really present. So the measurement is a part of the experiment. You see, what I like about physics the most is this sense of wonder, this sense of surprise. ठीक है, एक चीज होती है खाली इल्म, इल्म भी बड़ी अच्छी चीज है, लेकिन जब उसमें हैरत शामिल हो जाए, when you are surprised, when you have a sense of wonder, sense of surprise, then it becomes really interesting. तो इल्म के बाद हैरत आती है, हैरत के बाद अगली स्टेज आती है इश्क. ठीक है, जिसे अल्लामा इकबाल इश्क कहता है, जिसको पैशन कहते हैं. So this is something I really like about physics, is if you look at modern physics or quantum mechanics, it's so surprising that if you look at the moon should be different. If you don't look at the moon, it should be different. This is what quantum mechanics predicts. Now in this particular experiment, you just have one telescope that is being aimed at slit number 1, and there's no telescope here. So I give you half a minute to think about it. What's going to happen? Do you observe an interference pattern, or what's going to happen? Just think about it. Don't rush to conclusions. All right, any ideas? Please raise your hands.
One particle at a time?
Yeah, one particle at a time, doesn't really matter now. There's one particle at a time, say. And you're observing over a long interval of time. So it doesn't really matter whether there's one particle or many particles. If you have one particle, you just have to wait longer to observe an interference pattern. Please raise your hands if you think you know the answer or you can propose something. आप बताएं जी. चलो आप पीछे वाले बता दें. There will be an interference pattern. So it's partially correct. The answer is partially correct. It needs to be refined. The answer needs to be refined. आप बताओ.
I was thinking this would be a relation. Just
No.
so is it possible to have a single slit diffraction?
Yeah, in this case there is a single slit diffraction. Anyone? Avais?
But there will only be diffraction, no interference.
Then there's no difference between diffraction and interference. ये जो टेक्स्ट बुक्स में आता है ना, सिंगल स्लिट डायफ्रैक्शन और डबल स्लिट इंटरफेरेंस, there is diffraction occurring in the double slit experiment as well, and waves are interfering in the single slit experiment as well. So there's no difference. Tell me, what do you observe? Do you observe an interference pattern build up on the screen? No or yes? Partly? Partly? Yeah, partly. So what's going to happen here is something very interesting is going to happen. First of all, if this telescope clicks, this screen will not click. Right? There's a camera that is focused onto the entire screen. If this telescope is going to click, no photon or no electron will be observed on the screen, because the field has collapsed either onto the telescope or here. If it collapses as a particle onto the telescope, it can't be observed here. So when this telescope clicks, there is no question of seeing anything here. It's just going to be a background. No interference pattern will appear here. Okay? It's just going to be a background, a noisy smear of light. No interference pattern, no structure here. Okay? But if this does not click, we are still passing electrons through the apparatus. This electron does not click, which means there is a field and it's not collapsing at the telescope. So that field is then going to interfere with itself and going to form an interference pattern. So in a single event, of when this telescope clicks, if you sort out the outcomes, when this telescope clicks, nothing appears here. But when this telescope does not click, and you look at the photons that impinge on the screen, and you look over long intervals of time, an interference pattern will appear. So depending upon the condition when this telescope does not click, an interference pattern will gradually build up. Okay, so there are two types of outcomes. The first outcome is does T1 click? This is your question. And then I have two possibilities. Yes, no. Okay, this is how you draw flow charts in algorithms. Does T1 click? There are two possibilities, yes and no. If T1 clicks, and then you sort out those events, and you look at the screen, no interference pattern will appear. There's no fringes. However, if T1 does not click, and you look at the photons, when T1 has not clicked, you look at the photons that impinge on the screen, and you look at the screen, an interference pattern is going to build up. So you are sorting out the events in which T1 has not clicked, and when T1 does not click, you look at the screen, an interference pattern is going to build up. Because when T1 does not click, the wave function psi does not collapse in between the screens, and it has the full potential to give you interference. G.
So if T1 does not click, does that mean the electron passes through slit 2?
If T1 does not click, okay. If T1 does not click, it does not mean that the electron has passed through slit 2, because if the electron has passed through slit 2, an interference pattern cannot appear, because the electron has to pass through both of these slits at the same time. So really, this telescope has not collapsed the wave function. This is what is happening. This telescope has not collapsed the wave function, but if T1 does not click, it does not mean that the electron has passed through slit 2 and this telescope has missed the electron, because an interference pattern is observed, which means that even when T1 does not click, the electron is actually passing through both slits at the same time. There is a superposition. So this is the surprise of quantum mechanics. Okay? G.
Will this interference pattern be identical to that?
It's going to be identical. When T1 does not click, an interference pattern is observed. It's going to be identical. Will you have to wait longer to observe the same interference pattern? Yes. You'll have to observe longer, because there are some events in which T1 has clicked. So probably you'll have to wait twice as long. Alright, so do you remember the delayed choice experiment as well?
Yes.
Yes, alright. Now let's move on a little bit. And let's look at interference with a slightly more quantitative way. Now in between these slits, I'm going to tell you another very interesting experiment. In between these slits, there is a wave function psi. अब ये बड़े ध्यान से सुनना है, ये आपकी किताब में मौजूद नहीं है ये चीज, बल्कि इनमें से कुछ भी इस अंदाज में किताब में नहीं है, और किसी एक किताब में आपको नहीं मिलेगी ये बातें. देखो, in between these screens there is a wave function psi, which is a combination of two wave functions, psi1 and psi2, and I divide this by under root 2. I'll let you know why this under root 2 in a minute. Now, what is psi1 and what is psi2? Psi1 represents the wave function when the electron has assumedly passed through slit 1. Okay? And psi2 represents the wave function when the electron has assumedly passed through slit 2. So in between we have a combination of psi1 and psi2, which means that the electron is in fact passing through both slits at the same time, and you do not have any observer in this region. Okay? So since all of this is cluttered, I'm going to redraw this in a cleaner fashion. अब तो ये आदत सी हो गई है ये बना बना के. Some point here you have a wave function psi1 and you have a wave function psi2. And the total wave function inside this region is a combination, a sum of psi1 and psi2. And I divide by under root 2 as well. And the reason I'll let you know in a minute. Now let's suppose I close slit S2 and slit number 1 is open. This is what I will observe. And the wave function of the electron passing through slit 1 is psi1. Okay, only psi1 is the wave function that exists between screen A and screen B. Correct? Alright. This means, now this is a wave function. And this is your plane of observation. You're observing on this screen. Now if I take psi1, I take the modulus squared of this. This is the probability per unit length. Okay? And then I integrate. On the screen. I mean, I integrate all the way on the screen. What I would get is 1. Okay? Now if I perform this experiment with slit S1 closed and S1 open, what I'm going to observe is just a single slit diffraction pattern from this slit, and now the wave function is psi2. There is no psi1. Now for this psi2, if I would like to integrate psi2 over the screen, I should get 1. Now in this case, I have a combination of psi1 and psi2. Okay? Now if I would like to integrate psi1, just psi square dx over the screen, what should I get? I should get, what should I get? Aap bataye? 1. I should get 1. But psi equals psi1 plus psi2 over under root 2, which means if I take the modulus squared of this, I take the square of this, I get 1/2. Do you agree with me? I take the complex conjugate of this and multiply it with the original wave function. This is what I should get. नहीं समझ आई? इसकी समझ आई? If I take the modulus squared, psi mod squared, it's psi complex conjugate multiplied by psi. So what is the complex conjugate of this function? It's 1 over under root 2 psi1 star plus psi2 star. And what's the wave function? It's 1 over under root 2 psi1 plus psi2. Now I multiply all of this out, I get this. Okay? Now this term equals 0 and this term equals 0. I don't want to go into the details of why this term equals 0, this term equals 0. What I can tell is that these are orthogonal functions. But in any case, this term is 0, this term is 0. So my psi mod square is half psi 1 mod square plus psi 2 mod squared. Okay, because this term is 0 and this term is 0. Now if I integrate this term, over all of space, I have this 1/2 over all of space. This equals 1/2 plus 1/2 over the screen this is also over the screen. And what is this equal to? What is this integral equal to? 1. And what's this integral equal to? 1. So I have half 1 plus 1 half into 2 equals 1. So I do satisfy this requirement. But in order to satisfy this requirement, I must have a half here. And in order to have a half here, I must have a 1 over under root 2 here. So this 1 over under root 2 comes out of the normalization condition. And this is something you're learning in the tutorials this week. This is to conserve the probability, make the probability equal to 1. So what really is happening is that if you have both the slits open, then inside this region, you have electrons coming in. Inside this region, what you will have is a combination, is a field that spreads out in all of this space. Even if there's a single electron, it has a field that spreads out in all of this space, and that field has a mathematical form equal to psi 1 plus psi 2 over under root 2. And this field is called a superposition field. So these double slits are in fact creating a superposition. Okay? Which means it's creating both of these fields at the same time. The electron is passing through both slits at the same time. The photon is passing through both slits at the same time. So it exists in a superposition. And that superposition is being created by these two slits. And when you observe a particle on the screen, this superposition is going to collapse. This wave function is going to collapse. Now let me give you another example in order to bring this idea, in order to consolidate this idea. Another example, another disembarkation from the double slit experiment, we dissociate ourselves with the double slit experiment for a while and look at another physical experiment. We have a device that is called a beam splitter. ठीक है, और ये एक ऐसी डिवाइस है जो जिसके नाम में इसका काम पोशीदा है, यानी नाम को देख के बता सकते हैं काम क्या कर रही है। एक बीम आई फोटॉन्स की और वो उसको स्प्लिट कर देती है। ठीक है, फॉर एग्जाम्पल इफ यू हैव अ लाइट वेव कमिंग इन with a certain energy E, what this device is going to do is half of the energy is going to be transmitted and half of this energy is going to be reflected. So 50% of the energy is transmitted and 50% of the energy is reflected. Okay, so this is a beam splitter. It transmits 50% of the light and reflects 50% of the light. Now if the amplitude, one interesting question, if the amplitude of the incoming wave is A, what's the amplitude of the transmitted wave? Can you tell me what the amplitude is going to be? A over under root 2. It's not going to be A over 2. This amplitude is going to be A over under root 2 because energy is proportional to the square of amplitude. Okay, and this amplitude is also going to be A over under root 2. So this is a beam splitter. This is what a beam splitter does. It splits the wave into two waves. Half the energy is transmitted and half of it is reflected. Beam splitter. ठीक है, इसमें बामुसम्मा है, जो इसका नाम है वो इसका काम है। अब आप एक और एग्जांपल देखो, हमें पता है कि light acts as a wave and it also acts like a particle. So this light wave that is coming in is a stream of photons that comes in. अभी देखें, we are right at the depth of quantum mechanics. There are many students who take courses on quantum mechanics, many of those, but they don't understand what it really means. I'm not belaboring you with the mathematical calculations, I'm telling you what quantum mechanics really means. So now we have another beam splitter, and this light wave is in fact a stream of photons. We know that. Light can also be treated as photons. So we have a large number of photons that are coming in. Okay? Light of course travels in straight lines, so the photons are coming in, they're acting like particles coming in as straight lines, and per unit time there are n of these. So what's going to happen? Now in the particle picture, what's going to happen? आप बताएं what's going to happen? अब ये जो n photons आ रहे हैं beam splitter से आके टकरा रहे हैं, तो what's going to happen? How many of them will be transmitted? How many of them will be reflected? बताओ. n by 2 will be transmitted on average and n by 2 will be reflected. So we have some photons that will be transmitted and some photons that will be reflected, and this number on average is going to be n by 2 per unit time. This is going to be n by 2 per unit time. So these are identical photons all coming in. Of course all of them have the same speed, they have the same frequency, they have the same wavelength, so they are identical wavelengths. It's a monochromatic beam of photons. Okay, so if you have a detector here and you have a detector here, this is D1, detector 1, detector D2, And whenever a photon hits the detector, it clicks. And whenever, so per unit time, how many clicks will this detector see? N by 2. And per unit time, this detector will also see N by 2 clicks on average per unit time. ठीक है? तो ये एक ऐसा डिटेक्टर है जो एक सिंगल फोटोन को डिटेक्ट कर सकता है. ह्यूमन आई 40 या 50 फोटॉन्स पे ट्रिगर होती है रेटिना. 40 या 50 फोटॉन्स आके टकराएं तो रॉड्स जो रेटिना के अंदर सेल्स हैं, वो मॉलिक्यूल्स हैं, वो ट्रिगर होते हैं. ठीक है, लाइट सेंसिटिव. 40 या 50 फोटॉन्स. बाज ऐसे जानवर हैं, फॉर एग्जाम्पल द सबमरीन एनिमल्स लाइक ईल्स. These are these reptiles. Their retina are triggered by single photons because they are accustomed to live in the dark, and they would not like any photon to go amiss. Okay? They would like to be triggered by even very dim lights. So they are single photon sensitive. We can also have in the laboratory detectors that click whenever a single photon strikes them. Okay, and these detectors are called avalanche photodetectors, APDs. Anyway, this is an APD and this is an APD. Now let's look at another variant of this experiment. I have a beam splitter, and now instead of a stream of photons, a single photon comes in. And I have a detector D1, I have a detector D2. What's going to happen? Please think about it and I'll ask you what's going to happen. So quantum mechanics or modern physics is such that you can never take things for granted. So you have to think all the time. It's a photon, it's coming in, right? Just a single photon. जिस तरह मैंने बनाया है उसी तरह. All right. Please raise your hands. Chalo, don't raise your hand. I'll ask you what's going on. Because this is a question that everyone should know. So, आप बताएं क्या होगा? Shabash. There is an equal chance for both of these detectors to click, but at any one instant, will both the detectors click? No. So at any one instant, only one detector will click. Okay? At any one instant, one detector will click, but there's a 50% probability that this detector clicks and a 50% probability that this detector clicks. Okay? It's just like the double slit interference pattern, what you observe in this case. There's a 50% probability that this telescope will click, and a 50% probability that this telescope is going to click. But both of them are not going to click together. But you pass many electrons, some of the times this will click, some of the times this will click. And if you pass a large number of electrons or wait for long enough, half of them will register here and half of them will register here. So exactly this beam splitter is acting like a double slit. Even though the physical appearance is different, the concept is the same as a double slit. Okay, so 50% of the times this is going to click, 50% of the times this is going to click. Alright? But both of them will never click at the same time because a single photon cannot be split. Okay? Now let's build this concept a little bit further. In fact, I'm also teaching you quantum computing in disguise. रिमेंबर, अच्छा एक बात जरा गौर से देखें, दिस इज अ बीम स्प्लिटर, a photon that comes in here, तवज्जो से सुने प्लीज, a photon that comes in this path, in this port or path, can be reflected or it can be transmitted, but the photon can also come in through this path. Okay, and when it comes in through this path, it can either be reflected or it can be transmitted. So every beam splitter has two input paths or two input ports and two output ports. Okay, पोर्ट कहते हैं दरवाजे को, ठीक है, कराची की पोर्ट कासिम दरवाजा है पाकिस्तान का. तो इस बीम स्प्लिटर की दो इनपुट पोर्ट्स हैं और दो आउटपुट पोर्ट्स हैं. एवरी बीम स्प्लिटर हैज दिस. ओके, two input ports and two output ports. Now I'm going to draw an experimental arrangement which looks like this. I mean I have to draw it like थोड़ा सा नीचे करके बनाता हूँ. Now this is beam splitter 1. This is beam splitter 2. This is mirror 1 and this is mirror 2. And what mirror 1 does is that it totally reflects light. Okay? This is also a mirror. It totally reflects light. Now what I have is, I have a detector here, D3, and I have a detector here, D4. A single photon comes in. A single photon comes in, it encounters this beam splitter. Okay? So now my question is, which of these detectors will click? Draw the ray diagram, draw the diagram of the path of this photon. बताएं कौन सा डिटेक्टर क्लिक करेगा. दोनों डिटेक्टर क्लिक करेंगे. 50-50 तो प्रोबेबिलिटीज ऐड होके 1 होनी चाहिए. तो टोटल हाफ हो जाएगी.
सर
50-50 प्रोबेबिलिटी है. इक्वल प्रोबेबिलिटीज, Equal probabilities. Simultaneously click करेंगे.
नहीं सर. So 1 at a time.
First question. Can both of these detectors click simultaneously? No, because a photon cannot be split. There's one photon. Photon दो हिस्सों में नहीं बट सकता. It's fundamental. It cannot split. So both of these detectors cannot click at the same time. So there has to be a probability that D3 clicks, and there has to be a probability that D4 clicks. So both of these detectors cannot click. Only one can click. But what's the probability that D3 clicks? 50%, 50% here. Alright, so this is your classical common sense. And if I were in class 10 or class 11 or 12, I would also give the same answer. But what really is happening is that 100% of the time this detector is clicking, and 0% of the time this detector clicks. Now this I'm telling you as an experimentally observed fact. This is what really happens in the laboratory. So this is extremely baffling, extremely surprising. Now how do we explain this? We cannot deny what we observe. जो आप देखते हैं उससे तो इनकार नहीं कर सकते, ठीक है? क्योंकि साइंस इसी चीज का नाम है. What you observe is the truth. ठीक है? यकीन की आंख से आप देख रहे हैं. जो आप देख रहे हैं उसको नहीं आप डिनाई कर सकते. So this is an experimental outcome that 100% of the times this detector clicks, and never does this click. So you pass one photon, this detector clicks. You pass another photon, this detector clicks. Another photon, this detector clicks. Even though this is a beam splitter, this is a beam splitter. So what's happening here? So in order to explain this experimental outcome, one has to give an explanation. And the explanation goes as follows. Now this is a beam splitter. What you have here is that this beam splitter reflects and transmits. So now this single photon, classically you arrived at this answer because how did you arrive at this answer? You observed, you said that this photon can be reflected 50% of the times, and then it reflects from the mirror, and then it can be reflected or transmitted. So this is your first. So there are two possibilities here. ये बात गौर से सुने. आप 50% का रिजल्ट आपने कैसे निकाला? ऐसे निकाला. एक फोटोन आया. There is a 50% probability that it will be reflected. Then it goes here. It always goes here because it's always reflected from the mirror. Then there is a 50% probability that it goes here. 50% probability that it goes here. So the total probability that it goes here is 50% of 50%. It's 25%. And this is also 25%. Okay? But there are two more possibilities. The possibility is that this photon, instead of being reflected here, is transmitted. And what's the probability for this happening? 50%. Now after it hits this mirror, it goes up, and here it sees two scenarios. उसके सामने दो राहें हैं. ठीक है, एक ऐसे मकाम पे आ गए फोटोन की, उसको दो राहें नजर आ रही हैं इक्वल प्रोबेबिलिटीज की. अब it can either be reflected or transmitted. So it's reflected with a 50% probability, and it's transmitted with a 50% probability. But this 50% is 50% of this 50%. So this is 25%, and this is 25%. So the total probability that D4 clicks is 50% and the total probability that D3 clicks is 50%. This is how you arrived at this answer कि भाई 50% probability इसको click करने की है और 50% probability इसके click करने की है. So it clearly shows there's something wrong with this reasoning. Okay, there's something wrong with this. Ji.
Has it to do something with the specificity of how the photon behaves? Like if a certain photon has once reflected with a beam splitter, it always does that. Because if it does that, it will release D4. If it chooses to do a reflection and it reflects again, it will then release D4.
No, but a single photon is coming in. If a single photon coming in, it has to make up its mind here whether it wants to be transmitted.
Its mind, it never shifts.
No, it can shift. Why not?
That's a theory, sir.
No. It's not going to happen that way. It should never. Whenever it sees this beam splitter.
I'm just thinking.
No, it's not happening like that.
So when you put observer at D1,
Okay, I'll look at that again. Observer अभी खत्म होने का वक्त.
to get D1, if the electron transmits that, then it transmits through the other beam splitter again. And if it reflects from the first beam splitter, it reflects from the second.
That's my point.
No, that's not possible because if the photon or the electron sees this beam splitter, it's independent from a photon seeing this beam splitter. The same photon sees a beam splitter, then it sees another beam splitter. It cannot have a memory. No. The photon cannot have a memory. देखो आप कह रहे हो कि the photon must have a memory.
It has a mind, like when we see it, when we detect it, then it changes its mind, right?
It doesn't change its mind. We force it to behave something differently. So the photon cannot have a memory कि एक दफा के वो ट्रांसमिट हुआ तो अगली दफा भी वो ट्रांसमिट होगा. इसको एक्सप्लेन कैसे करते हैं इस आउटकम को? इसको एक्सप्लेन यूं करते हैं. अब देखें. आपका वैसे पॉइंट बहुत अच्छा है. दिस इज द वे टू थिंक. So a photon comes in. Instead of thinking in this fashion that this photon either goes here or is transmitted. This is the classic way of thinking about the photon, that the photon can either be transmitted or reflected, or the electron in a double slit experiment can either go through slit 1 or slit S2 because the electron cannot be split. What is it doing? It is taking both of these paths at the same time. It's in a superposition, in other words. So instead of saying that this photon is either transmitted, phone को छोड़ दें, is either transmitted or reflected, what we say is that the photon is both transmitted and reflected at the same time. And it's in a superposition. So if I call this part 1, there is a wave function associated with this part. I call it psi 1. And there is a wave function associated with this part. I call it psi 2. So in between this beam splitter B1 and B2, what we have is a superposition of both of these paths. This photon is taking both of these paths at the same time. But remember, it doesn't mean being split. It is taking both of these paths at the same time, just like the double slit interference pattern. Since this is a double slit, this is equivalent to a double slit, this is the screen. This is equivalent to what you observe here is equivalent to what you see on the screen. After the first double slit or the first beam splitter, the photon has to be in a superposition state. So it has a field that fills up this entire region. You don't know where the photon is. You don't know which path the photon is taking. It's in a superposition state, and its total wave function inside this regime is psi1 plus psi2 over under root 2. Alright? Now if you place your detector, if you would like to find out which path the photon has taken, you place a detector here and you place a detector here. Then this superposition will collapse. Okay? And if you have a detector here, D3 and D4. Okay, very interesting observation. This is D1, D2. अब इस बात को आपने बड़े ध्यान से सुनना है, कोलैप्स का मतलब समझ आ जाएगा. If you do not have these detectors, this detector clicks 100% of the time. Okay? Now you sneak in these observers in this path. You break open the black box and place your detectors here, because you have a gut feeling that the photon is passing through both slits at the same time. So let's put in detectors to see which path the photon is taking. So you sneak in detectors and place them here, one in path 1 and the other in path 2. Now what's going to happen is that D1 clicks with 50% probability and D2 clicks with 50% probability, and nothing is seen here because the photon has expended all its energy in producing a click on a detector. So the photon produces a click on D1 with 50% probability and a click on D2 with 50% probability, but it never produces a click on both of these. So you are once again dumbfounded, because the photon has actually, by placing detectors, you claim that the photon is not passing through both slits at the same time, it is passing through one slit. But if you remove these detectors, only this detector clicks. So the photon has to go through both slits at the same time. It's the same paradox that we observed in the double slit experiment. Okay, so if you want to observe the path of the photon, this wave function collapses. Either you will observe the path to be psi1 or you will observe it to be psi2. That is, the photon will either take path psi1 or psi2. Let me just finish, please. So, alright, so this is the collapse of the wave function. So this effect appears that D3 clicks 100% of the times only when you do not have any detectors here. Only when you keep the superposition, this superposition intact. Now how do we explain that 100% of the photons land onto this detector? Now what a beam splitter does, a beam splitter does the following. You have a wave function psi1. Now how many input ports do you have? 2. So if the wave input is psi1, then what a beam splitter does is it produces psi1 plus psi2 over under root 2. So horizontal paths of the photon, I denote them as 1. So this is path 1. Okay? I mean, let's not call it horizontal paths. There are two kinds of paths, psi1 and psi2. And if in the input the photon is coming in along a horizontal path, its path, let's call it A. Or let's call it, still call it 1, it doesn't matter really. Let's call it 1. So if a photon comes in through an input port like this, the beam splitter converts it into a superposition. This dhyan se sunna hai. If a photon comes in along a horizontal path, strikes the beam splitter makes a superposition out of it. Okay? If the photon comes in through this path, say, through path psi2 or through path 2, and the photon sees the same beam splitter, it produces a superposition psi1 minus psi2 over under root 2. There is a difference of a minus sign here. So this is also a superposition, this is also a superposition. Here psi2 has a different phase. The phase of this is pi. Exponent I, pi is minus 1. Okay? So now what we have here, we can explain the outcome using this formalism. Just a couple of minutes. This is your input photon, psi1. It sees this beam splitter, B1. It goes into a superposition. Okay? It goes into a superposition. It is taking both of the parts at the same time. I can also write this as 1 over under root 2 psi1 plus psi2. And now this superposition, this entire field sees a second beam splitter. This entire field sees a second beam splitter. So I apply the second beam splitter onto this wave function. Now what this wave function does, what this beam splitter does nothing to the 1 over under root 2. What does it do to psi1? The beam splitter acting on psi1 produces this. So B2 acting on psi1 produces psi1 plus psi2 over under root 2. And B2 acting on psi2 gives you this. So B2 acting on this produces psi1 minus psi2 over under root 2. Now I can do some simple algebra. This psi2 cancels out. And my final result is psi1 2 times psi1 over 2, which is psi1. So my output is along, say, either D3 or D4, say D4, and it clicks with 100% probability, and D3 clicks with 0% probability. So I'm producing just psi1, which is a photon that is coming out in a horizontal path. So only this detector clicks. And this can only be explained if a superposition exists here and the beam splitter is producing superpositions of this kind. So inshallah, see you on Thursday. And Thursday is a very important class. We'll have a demonstration inside the class and we'll start our discussion of the Schrodinger equation.